Here we've got a nice short question on an optical fibre. So you might remember that our optical fibres have a structure as such. This is looking end on as if I've cut through it. I've got my core, I've got my cladding, and that whole thing is surrounded by a protective outer sheath. So I've got my core, my cladding, and a protective outer sheath. And the sheath, its main job is just to protect the fibre from things like scratches and stuff like that. It's also got a secondary function, which is any light that might be leaking out from this cable. It stops it being transmitted into another cable, but that's not so important. If you're ever asked what the purpose of the outer sheath is, always say to protect the fibre. Then, in this second part of the question, we're told that for one particular fibre, the speed of monochromatic light in the core is 1.97 times 10 to the 8, and in the cladding is 2.03 times 10 to the 8. Now, I always like to draw this out just to help me with this. We're trying to calculate what the critical angle, theta c, is for the interface between the core and the cladding. So here's my core, here's my cladding, here's my normal. We want to be calculating theta c, the critical angle, that the incoming ray makes with the normal at the point of which it gets totally internally reflected, or that is where the angle of refraction is 90 degrees. So we know from Snell's law that n1 sine theta 1, where n1 would be the refractive index of the core, is equal to n2 sine theta 2, where n2 is the refractive index of my cladding. Well, sine of theta 2 becomes sine of 90, which just becomes 1. So I can rearrange this to say, okay, therefore, sine of the critical angle is equal to n2 over n1. But that means that I do need to work out the refractive indices of each of these. Well, refractive index is speed of light in a vacuum over speed of light in the material. So for n1, which is our core, that's this one here. So that'll be 3 times 10 to the 8. Remember, our refractive index always has to be above 1, and it's a ratio of the speed of light in a vacuum to the speed of light in the material. So for n1, it's 3 times 10 to the 8 over 1.97 times 10 to the 8, and that gives us a refractive index of 1.52. Remember, there's no units on refractive index, it's just a ratio. And then for n2, same again, c over v is equal to 3 times 10 to the 8 over 2.03 times 10 to the 8, and that gives us a refractive index of 1.48. So once I've got my two refractive indices here, I can check that makes sense. For total internal reflection to occur, I must be going from more optically dense to less optically dense. So I must be going from a higher refractive index of 1.52 to a lower one here. Yes, that tallies out. So then I can finish off my equation here and say, okay, in that case, theta c, my critical angle, is going to be equal to sine to the minus 1 on my calculator of n2 over n1. So that's 1.48 over 1.52. And when we plonk those numbers into our calculator, we get an answer of 76.8 degrees. Always worth drawing a little diagram to give you the opportunity to work out what's going on.